9.46 trillion kilometers. That is the distance of 1 light-year. Not a rough estimate, not a rounded figure chosen for convenience, but the precise measurement of how far light travels through the absolute vacuum of space in the span of exactly 1 Earth year. 9,460,000,000,000 kilometers. Written out in its full numerical form, 9,460,000,000,000 kilometers. It is a number so staggeringly large that the human mind, shaped by evolution to understand distances measured in footsteps and river crossings, encounters it and immediately begins to flinch, to reduce it, to translate it, to wrap it in metaphor and comparison until it becomes something that feels familiar and manageable. But that flinching is exactly what we must resist, at least for now, because before we can truly understand interstellar space, before we can appreciate the profound scale of the cosmos, the distance to even our nearest stellar neighbor, or the monumental and perhaps insurmountable challenge of genuine human interstellar travel, we must first sit with this number and feel its full, uncompromising weight. Let us begin not in the vacuum of space, not in the realm of physics equations and theoretical propulsion systems, but here on the surface of the Earth, where all of our deep instincts about distance were first formed and sharpened over hundreds of thousands of years of human evolution. You are walking down a city street at a comfortable, average human walking pace, 5 kilometers per hour. This is the speed at which our species first moved across this planet, the speed of the hunter-gatherer following seasonal migrations, the pilgrim walking to a sacred site, the explorer crossing unfamiliar terrain on foot. 5 kilometers per hour is the pace at which Homo sapiens populated every continent on Earth, crossed land bridges that no longer exist, and spread from a single point of origin in Africa to every corner of the globe. At 5 kilometers per hour, how long would it take you to walk 1 light-year? The calculation is disarmingly simple, and its result is absolutely devastating. 1 light-year is 9,460,000,000,000 kilometers. Divide that by 5 kilometers per hour, and you get approximately 1,892,000,000,000 hours of continuous walking. Convert those hours into years. There are 8,766 hours in a calendar year, and you arrive at roughly 215,800,000,000 years. 215,800,000,000 years. To walk a single light year at a comfortable human pace would require more than 200 billion years of uninterrupted walking. Not merely walking every day, but walking every hour of every day, through the nights, through every season, through every storm and heat wave, without a single pause for sleep or food or rest. For context, the entire estimated age of the observable universe is approximately 13.8 billion years. Walking 1 light year would consume more than 15 times the current age of the universe. If you had started walking at the precise moment of the Big Bang itself, when the first protons and neutrons formed from the cooling quark-gluon plasma, before stars existed, before galaxies existed, before planets or moons or any solid surface to walk upon existed, you would not yet have covered even 7% of the distance the universe would have undergone its entire history of star formation, galaxy assembly, the birth and death of countless stellar generations, the formation of our own solar system, the emergence and evolution of all life on Earth, the entire span of human civilization from the first stone tools to the digital age, and you would still be profoundly, laughably, heartbreakingly far from your destination. This is not merely a large number. This is a number that reveals something categorical and fundamental about the nature of space itself, that the cosmos is structured at a scale for which human bodies, human lifetimes, and human intuitions were never designed and never equipped to navigate. But perhaps walking is an unfair starting point. Humans, after all, are not limited to the pace of unassisted bipedal locomotion. We are a species defined by our ingenuity. We build machines. We accelerate beyond our biology. We have automobiles. Consider a modern highway car traveling at a comfortable cruising speed of 100 kilometers per hour. This is the speed limit on many major motorways across Europe, North America, and Asia. The ordinary speed of millions of daily commuters and intercity travelers. It is fast enough to feel genuinely quick when you are experiencing it, fast enough that the landscape blurs past at a satisfying rate. At 100 kilometers per hour, driving continuously and without a single stop, no fuel, no maintenance, no sleep, no deviation, the journey of 1 light year would take approximately 94,600,000,000 hours. Divide that by the hours in a year, and you arrive at just over 10,790,000,000 years, approximately 10.79 billion years. The universe itself is only about 13.8 billion years old. A car at highway speed would need a journey lasting nearly 80% of the age of the universe to cover 1 light year. Even if we were to imagine the fastest production sports car ever manufactured, something engineered to sustain 400 kilometers per hour on a perfectly straight, infinite road, the travel time would still be roughly 2.7 billion years. The Earth itself is only 4.5 billion years old. Our planet formed from the collision of dust, rock, and gas swirling in a protoplanetary disk around our young sun. Life appeared on Earth perhaps 3.7 billion years ago in the form of simple single-celled organisms. Multicellular life only became complex and diverse approximately 600 million years ago. A sports car at top speed, running since before a single living cell existed on Earth, would not yet have completed the journey of 1 light year. Let us escalate further. A commercial passenger aircraft, the kind that carries roughly 4 billion people across intercontinental routes every year, the kind so ubiquitous that most of us give barely a passing thought to the miracle of being suspended 6 miles above the surface of a planet, hurtling through the upper atmosphere at nearly the speed of sound, cruises at approximately 900 kilometers per hour. This is the standard cruising speed of a Boeing 737, an Airbus A320, or any of the wide-body jets that form the backbone of modern aviation. At 900 kilometers per hour, maintaining absolute constant speed for the entire journey, traveling 1 light year would take approximately 1,199,000,000 years, nearly 1.2 billion years. That is more time than separates us from the formation of the first complex, visually sophisticated animal eyes. It is more than twice the time that has elapsed since the great oxygenation of Earth's atmosphere, the event that made complex aerobic life possible. A commercial aircraft flying from the moment that oxygen first began accumulating in Earth's atmosphere would still not have finished the journey. Now, let us consider high-speed ground transport at its most extreme. The fastest operational high-speed rail systems, including the TGV network in France, the Shinkansen in Japan, and the high-speed rail network in China, achieve regular commercial service speeds of around 300 to 350 kilometers per hour. In 2019, Japan's experimental maglev train achieved a world record of 603 kilometers per hour in a test run. At 603 kilometers per hour, traveling 1 light year non-stop would take approximately 1,789,000,000 years, still nearly 1.8 billion years, still a number that mocks the idea of a journey. The supersonic aircraft represents a significant step change. The Concorde, which served transatlantic commercial passengers for 27 years before its retirement in 2003, cruised at approximately Mach 2.04, which corresponds to roughly 2,180 kilometers per hour at altitude. Passengers aboard Concorde could cross the Atlantic Ocean in about 3.5 hours, a journey that takes the average subsonic airliner about 7 to 8 hours. Concorde was genuinely extraordinary, and its retirement remains a source of nostalgia for many who love the idea of compressing distance through speed. At 2,180 kilometers per hour, a non-stop journey of 1 light year would take approximately 495 million years, nearly 500 million years. Not quite as catastrophic a figure as the ones we have been dealing with, but still immense beyond meaningful comprehension. The military domain has pushed further. The SR-71 Blackbird, operated by the United States Air Force from 1966 to 1999, and universally regarded as one of the most extraordinary aircraft ever built, holds the official air-breathing jet aircraft speed record at approximately 3,529 kilometers per hour, roughly Mach 3.3. This aircraft was designed to fly so high and so fast that it could not be intercepted by any surface-to-air missile or fighter jet in any nation's arsenal. It leaked fuel on the ground because its titanium skin was designed to expand and seal in flight from the heat of air friction. It is an icon of what human engineering can achieve within conventional atmospheric flight. At 3,529 kilometers per hour, a journey of 1 light-year would take approximately 305 million years. 305 million years. Dinosaurs first appeared on Earth approximately 245 million years ago and went extinct about 66 million years ago. An SR-71 Blackbird flying at full speed since before the first dinosaur ever walked the Earth would still not have completed the journey. We have now thoroughly exhausted the full spectrum of conventional human transportation, from the pace of a walking human to the fastest air-breathing aircraft ever flown. And across this entire range of speeds, covering a factor of more than 700 in velocity from walking pace to SR-71 speed, we have succeeded only in reducing the travel time from 215 billion years to 305 million years. We are still talking about timescales that make all of human history, all of human civilization, all of human prehistory look like the briefest of moments. The fundamental problem has not changed. It has merely been illustrated from different angles. We turn, therefore, to spacecraft, the fastest objects that humans have ever actually built, launched, and sent beyond our world. On September 5, 1977, NASA launched Voyager 1 from Cape Canaveral, Florida, atop a Titan IIIe Centaur rocket. The mission's primary objective was to perform close flyby observations of Jupiter and Saturn, returning detailed images and scientific data from the outer solar system for the first time. But from the beginning, the Voyager missions carried a deeper significance: the awareness that these spacecraft, after completing their planetary surveys, would continue on indefinitely into interstellar space, becoming the first human-made objects to leave the solar system entirely. Voyager 1 crossed the heliopause, the boundary at which the solar wind gives way to the interstellar medium, the region where the sun's influence effectively ends, in August 2012, at a distance of approximately 121 astronomical units from the sun. 1 astronomical unit is the average distance from Earth to the sun, roughly 150 million kilometers. So the heliopause crossing occurred at about 18.15 billion kilometers from the Sun. As of the early 2000s, Voyager 1 is the most distant human-made object ever, at a distance exceeding 23 billion kilometers from the Sun and increasing every day. Its current speed relative to the Sun is approximately 17 kilometers per second. This translates to about 61,200 kilometers per hour, or roughly 1.47 billion kilometers per year. At that speed, a Voyager 1 would take approximately 73,600 years to travel 1 light-year. 73,600 years. This is the first figure in our exploration that feels qualitatively different from everything that came before. For the very first time, we are not talking about geological timescales or evolutionary timescales. We are talking about something that fits, barely, tenuously, within the general frame of human civilization. The oldest cave paintings, at Chauvet-Pont d'Arc in southern France, are roughly 36,000 years old. At Voyager's speed, our spacecraft would cover half a light-year in the time separating us from those ancient artists pressing their hands against stone walls and blowing pigment through hollow bones. And yet, even this improvement is insufficient for any plausible crewed mission. 73,000 years is roughly 12 times the length of all recorded human history. The agricultural revolution that transformed our species from nomadic hunter-gatherers to settled farmers began only about 10,000 years ago. Writing was invented perhaps 5,000 years ago. The entire sweep of human civilization, from Sumer and Egypt to the modern digital world, fits within 1/14 of a Voyager speed journey to to a single light year. No crew could survive such a voyage. No mission architecture could maintain coherence across such timescales. A Voyager 1 did not leave Earth with this speed directly from its engines. It achieved its remarkable velocity in part through planetary gravity assists, slingshot maneuvers past Jupiter and Saturn that essentially stole a small amount of orbital momentum from those giant planets and transferred it to the spacecraft. This technique, first proposed seriously by aerospace engineer Gary Flandreau in 1965, has been used in virtually every outer solar system mission since and represents one of the most elegant applications of orbital mechanics in the history of spaceflight. The New Horizons spacecraft, launched in January 2006 on a mission to perform the first close flyby of Pluto and the Kuiper Belt, was the fastest spacecraft ever at launch, achieving an initial velocity of approximately 16.26 kilometers per second after its Atlas V rocket and Star 48B upper stage firings. New Horizons flew past Jupiter in February 2007, gaining additional speed through a gravity assist that brought its heliocentric velocity to approximately 23 kilometers per second at the time of the Jupiter encounter. After the gravity assist, and as it climbed away from the Sun, New Horizons slowed, as all spacecraft must when moving against the pull of solar gravity. Its current speed in the outer solar system is approximately 14 kilometers per second. At that velocity, traveling 1 light year would take approximately 21,000 to 22,000 years, depending on the exact reference frame and trajectory considered. But nothing built by human hands has ever moved as fast as the Parker Solar Probe. The Parker Solar Probe was launched on August 12, 2018, with a mission unlike anything previously attempted. Rather than traveling outward into the cold, distant regions of the solar system, it was designed to travel inward toward the Sun itself, ultimately diving into the outer layers of the solar corona, the Sun's superheated upper atmosphere, which reaches temperatures exceeding 1 million degrees Celsius. Understanding the mechanisms by which the corona reaches such extreme temperatures and by which the solar wind is accelerated to its observed speeds required getting close in a way no spacecraft had ever managed before. To achieve the remarkably close solar approaches needed for its scientific mission, the Parker Solar Probe uses a series of Venus gravity assists, 7 in total across its mission, to gradually lower its orbital perihelion, bringing it progressively closer to the Sun with each successive orbit. On its final planned closest approaches, the spacecraft will pass within approximately 6.16 million kilometers of the Sun's photosphere, about 9 solar radii. At these close distances, the spacecraft's velocity, relative to the Sun, reaches extraordinary values, governed by the conservation of angular momentum in its highly elliptical orbit. During its record-setting close approach, the Parker Solar Probe has achieved speeds of approximately 163 kilometers per second, roughly 587,000 kilometers per hour. This is approximately 0.054% of the speed of light, and it is the fastest speed any human-made object has ever attained relative to the Sun. 163 kilometers per second. Let that number settle for a moment before we continue. In a single second, the Parker Solar Probe covers 163 kilometers, roughly the distance from London to Birmingham, or from New York City to Philadelphia. In a single minute, it covers nearly 10,000 kilometers, roughly the distance from New York to Moscow. In an hour, it covers more than 500,000 kilometers, more than the distance from Earth to the Moon in both directions. And yet, at this extraordinary speed, traveling 1 light year would still require approximately 17,900 years. 17,900 years. It is the fastest any physical object built by humans has ever traveled, and it would still require a span of time nearly 3 times the length of all recorded human history to cross a single light year. This is the fundamental reality with which we must contend, not a temporary technological limitation awaiting an engineering solution, but a statement about the relationship between the distances of the cosmos and the energies available to any civilization, operating within the constraints of known physics. To understand why these numbers are so extreme, and to understand what it would actually take to cross a light year in any time frame that would be meaningful to a human being, we need to understand the physics that governs the maximum possible speed, the speed of light, and the deep structure of the universe that enforces it as an absolute limit. Light traveling through the vacuum of space moves at exactly 299,792.458 kilometers per second. This is a measured, defined value, so precisely known that it is now used as part of the formal definition of the meter in the International System of Units. In 1 second, and a photon of light travels a distance equivalent to roughly 8 times the circumference of the Earth. In 8 minutes and 20 seconds, light travels from the Sun to the Earth, a distance of approximately 150 million kilometers. In 1.3 seconds, light travels from the Earth to the Moon. In 4.24 years, light travels from the Sun to Proxima Centauri, our nearest stellar neighbor. This is what it means for Proxima Centauri to be 4.24 light-years away. It is the distance that light, the fastest thing in the universe, covers in 4.24 years of constant travel. Astronomers use light-years as their fundamental unit of interstellar distance, not out of habit or convenience, but because the scale of the cosmos is naturally expressed in terms of the time required for light to traverse it. Using kilometers for interstellar distances is possible, but the resulting numbers are so large as to be nearly meaningless to human intuition. Saying that Proxima Centauri is 40 quadrillion, 208 trillion kilometers away is technically accurate, but psychologically inert. Saying it is 4.24 light-years away carries an immediate implication. Even light needs more than 4 years to make that journey. For a species accustomed to near instantaneous global communication, this is a sobering statement. But the speed of light is not merely a practical yardstick for astronomers. It is a fundamental constant of nature, symbol C in the language of physics, woven into the deepest structure of the universe in a way that transcends any particular physical phenomenon involving electromagnetic radiation. It is the speed at which all massless particles must travel, and the speed at which no massive object can ever arrive. It appears in Einstein's famous equation relating energy and mass. It is the speed at which gravitational effects propagate. It is the speed of causality itself, the maximum rate at which any cause can produce any effect anywhere in the universe. The speed of light is not a technological limit. It is a law of nature. This understanding was not always in place. For most of human intellectual history, the speed of light was assumed to be either infinite or simply so fast as to be effectively instantaneous. The Danish astronomer Ole Rømer provided the first solid observational evidence that light had a finite speed in 1676, using discrepancies in the observed timing of eclipses of Jupiter's moon, Io, to estimate a value that was remarkably close to the modern measurement, within about 25%. Over the following 2 centuries, increasingly precise measurements refined the value, but it was not until Albert Einstein's Annus Mirabilis of 1905 that the full physical significance of the speed of light was understood. Einstein's special theory of relativity, published in June 1905 in the journal Annalen der Physik, begins from 2 foundational postulates. The first, the laws of physics are identical for all observers moving at constant velocity relative to one another. There is no preferred reference frame, no absolute rest. The second, the speed of light in a vacuum is the same for all such observers, regardless of the motion of the light source or the observer. This second postulate is the revolutionary one, and its apparent simplicity conceals an extraordinary depth of implication. Imagine you are standing on a railway platform as a train passes at 200 kilometers per hour. A passenger on the train throws a ball forward at 50 kilometers per hour relative to themselves. From your perspective on the platform, the ball is moving at 250 kilometers per hour. The speeds simply add. This is Galilean relativity, the physics of everyday intuition, and it is correct at the velocities we encounter in ordinary life. But apply the same logic to light, and the universe refuses to cooperate. An astronaut on a spacecraft moving at half the speed of light shines a flashlight forward. The photons from that flashlight do not travel at 1.5 times the speed of light as seen from Earth. They travel at exactly the speed of light. The speeds do not add. Light always moves at light speed, relative to every observer, regardless of relative motion. This is what Einstein's postulate demands, and it is what experiment confirms. For this to be true, something else must give. The something else, the flexible, elastic thing that adjusts to preserve the constancy of the speed of light, is space and time themselves. Time does not flow at the same rate for all observers. Space does not have the same extent for all observers. These quantities are relative. They depend on the observer's state of motion. And this relativity of time and space is not a philosophical abstraction or a mathematical trick. It is a physical reality with measurable, confirmed consequences. The phenomenon of time dilation, the slowing of time for moving objects relative to stationary observers, has been confirmed experimentally in numerous ways. In 1971, physicists Joseph Haffel and Richard Keating flew extremely precise atomic clocks around the world on commercial aircraft and compared them to stationary reference clocks. The traveling clocks showed measurably less elapsed time, exactly as special relativity predicted. GPS satellites require relativistic corrections to their onboard clocks to maintain the timing accuracy necessary for the system to function. Without these corrections, GPS positions would drift by several kilometers per day. Every time a GPS system on your phone gives you an accurate position, it is doing so with the help of Einstein's relativistic equations. Time dilation is not a theoretical curiosity. It is something our civilization has built infrastructure around. The mathematical quantity that captures the degree of time dilation at a given speed is called the Lorentz factor, usually denoted by the Greek letter gamma. It is defined as 1 divided by the square root of the quantity 1 minus v squared over c squared, where v is the velocity of the moving object and c is the speed of light. When v is small compared to c, as it is for everything in ordinary human experience, the Lorentz factor is essentially equal to 1, and time dilation is negligible. But as v approaches c, the denominator approaches 0, and the Lorentz factor approaches infinity. This exponential divergence near the speed of light is what makes relativistic travel so counterintuitive and so physically extreme. At 10% of the speed of light, 29,979 kilometers per second, the Lorentz factor is approximately 1.005. Time aboard a spacecraft moving at this speed passes about 0.5% more slowly than for a stationary observer, barely noticeable. At 50% of the speed of light, the Lorentz factor is approximately 1.155, but time passes about 15% more slowly. At 90% of the speed of light, the factor is approximately 2.29. Time passes at less than half the rate experienced outside the spacecraft. At 99% of the speed of light, the Lorentz factor is approximately 7.09. 1 year of shipboard time corresponds to just over 7 years in the external universe. At 99.9%, the factor is 22.4. At 99.99%, it reaches approximately 70.7. At 99.9999%, 6 nines, the Lorentz factor exceeds 700. What does this mean physically in the context of traveling a light year? At 99% of the speed of light, the journey of 1 light year from the perspective of an external observer takes approximately 1.01 years. But from the perspective of a crew aboard the spacecraft, with their internal time running at 1/7.09 of the external rate, the journey would subjectively take only about 52 days. At 99.99% of the speed of light, the external journey still takes slightly over 1 year, but the crew experiences only about 5 days. The light year, that seemingly impenetrable gulf of 9.46 trillion kilometers, becomes, for a traveler moving at sufficiently relativistic speeds, a voyage of days. And because the Lorentz factor grows without bound as speed approaches c, there is in principle no limit to how much a sufficiently fast traveler could compress their experience of time. At high enough speeds, a human being could theoretically traverse the entire observable universe within a single lifetime of subjective experience. This seems to offer a door through the otherwise impassable wall of interstellar distance, but the door has a price, and the price is stamped on it in the language of physics and engineering. The core of the problem is the rocket equation, the Tsiolkovsky equation, named for the Russian scientist Konstantin Tsiolkovsky, who derived it in 1903 at the very dawn of the space age. The rocket equation states that the achievable change in velocity of a spacecraft is equal to the exhaust velocity of its propulsion system, multiplied by the natural logarithm of the ratio of the spacecraft's initial mass to its final mass. In plain language, to go faster, you need either a more energetic exhaust or more propellant. The relationship between additional velocity and required propellant mass is exponential, not linear, and every additional unit of speed requires proportionally more propellant than the last. This is the tyranny of the rocket equation, and it is one of the most relentless constraints in all of aerospace engineering. For chemical rockets, the kind that have powered every human space mission from Mercury to Artemis, the exhaust velocity is limited by the chemical energy available in the propellant. The most energetic chemical combination is liquid hydrogen and liquid oxygen, so used in engines like the RS-25 and the RL-10, which achieves a specific impulse of around 450 seconds, corresponding to an effective exhaust velocity of about 4.4 kilometers per second. To accelerate a spacecraft to 1% of the speed of light, approximately 2,998 kilometers per second, using a chemical rocket would require a mass ratio so astronomical as to be physically impossible. The calculation gives a mass ratio on the order of 10 to the power of 295. For reference, the observable universe contains approximately 10 to the power of 80 protons. The required rocket could not be built from all the matter in the observable universe combined. Nuclear propulsion offers a significant improvement. The NERVA nuclear thermal rocket program, which developed and tested flight-ready nuclear thermal engines in the United States between 1955 and 1972, demonstrated engines with specific impulses of around 800 to 900 seconds, roughly double the efficiency of the best chemical rockets. This improves the mass ratios considerably, but still falls catastrophically short of what relativistic travel requires. Is nuclear pulse propulsion the concept explored most seriously under Project Orion in the late 1950s and 1960s? Offers a further order of magnitude improvement by detonating nuclear bombs directly behind the spacecraft and capturing the impulse on a massive pusher plate. The effective exhaust velocity of a well-optimized nuclear pulse drive could potentially reach 10,000 to 30,000 kilometers per second, several percent of the speed of light. This brings the mass ratio for an interstellar mission into the range of the merely enormous, rather than the cosmically impossible. Project Orion studies in the 1960s concluded that a spacecraft of perhaps 400,000 metric tons, carrying enough nuclear pulse units for the journey, could potentially reach nearby stars in 133 years at a cruise speed of around 3% of the speed of light. At 3% of the speed of light, 1 light year would take approximately 33 years. The propulsion concept with the highest theoretical specific impulse accessible with known physics is the antimatter annihilation drive. When a particle of matter meets its corresponding antiparticle, a proton meeting an antiproton, an electron meeting a positron, the two annihilate completely, converting entirely into energy. The energy released per unit mass is far greater than any nuclear reaction. E equals mc squared, with 100% of the rest mass energy released, rather than the fraction of a percent achieved in fission, or the fraction of a percent per nucleon achieved in fusion. An antimatter rocket that could channel the annihilation products, primarily pions and gamma rays, as directed thrust could theoretically achieve specific impulses comparable to a significant fraction of the speed of light. In principle, an antimatter rocket with a relatively modest mass ratio could accelerate a crew to 50, 70, or even 90% of the speed of light, making the journey to Proxima Centauri a voyage of years rather than generations. The obstacle is production. Antimatter does not exist naturally in any useful quantity accessible to us. It must be created in particle accelerators, where high-energy collisions produce matter-antimatter pairs. The world's most powerful such facility, CERN's Large Hadron Collider Complex in Geneva, produces a few nanograms of antihydrogen and antiprotons per year at a cost in energy and infrastructure running to billions of dollars. A single interstellar mission using antimatter propulsion would require millions of metric tons of antimatter. At CERN's current production rates, accumulating that amount of antimatter would take vastly longer than the current age of the universe, and the storage of antimatter, which annihilates on contact with any ordinary matter container, presents an engineering challenge of its own that remains entirely unsolved at meaningful scales. Another serious and genuinely innovative approach to near-light speed travel was proposed in the 1960s by physicist Robert Bussard in the form of the ramjet concept. The Bussard ramjet envisions a spacecraft with an enormous electromagnetic scoop, perhaps hundreds or thousands of kilometers in diameter, that gathers interstellar hydrogen as it travels and uses it as fuel for a fusion reactor. This would eliminate the need to carry propellant, sidestepping the rocket equation's tyranny entirely. In theory, a Bussard ramjet could accelerate indefinitely, approaching the speed of light asymptotically and enabling travel across galactic distances within human lifetimes. Unfortunately, subsequent analysis has revealed serious problems with the concept. The density of interstellar hydrogen is extremely low, about 1 atom per cubic centimeter in the vicinity of our solar system, meaning the scoop would need to be impractically vast to gather sufficient fuel. The electromagnetic drag produced by the scoop would likely exceed the thrust generated, making acceleration impossible rather than sustained, and the catalytic fusion of proton-proton chains required to fuse interstellar hydrogen at the required rates has not been demonstrated in any laboratory context. The Bussard ramjet remains a beautiful idea that has not survived closer scrutiny. More recently, the Breakthrough Starshot initiative, announced in April 2016, proposed an approach that sidesteps the mass problem entirely by eliminating the crew. The concept involves accelerating extremely small spacecraft, wafer-sized probes weighing perhaps a few grams, carrying miniaturized cameras, sensors, and communication equipment, using powerful ground-based lasers focused on ultra-thin reflective sails. A laser array of perhaps 100 gigawatts, firing for a few minutes, could theoretically accelerate such a light sailcraft to approximately 20% of the speed of light. At that speed, the journey to Alpha Centauri, the triple star system that includes Proxima Centauri, 4.37 light-years away, would take approximately 20 years. 1 light-year would be traversed in about 5 years. The engineering challenges are formidable, but arguably within the realm of technologies we can currently conceive. Phased laser arrays, ultralight nanoscale sail materials, miniaturized electronics capable of surviving decades of interstellar travel, and directional antennas capable of transmitting data back to Earth from 4 light-years away at useful data rates. No crew lives or dies on this mission. The starships would not decelerate at their destination. They would fly through the target system at 20% of the speed of light, snapping photographs and transmitting data in the brief hours of their closest approach. And then they would continue into the dark, unrecoverable, on a journey that will last for geological timescales. Even setting aside the question of propulsion, a human being traveling near the speed of light would face threats that have nothing to do with the engines powering the spacecraft. The interstellar medium, the tenuous material that fills the space between stars, is not truly empty. It is a diffuse mixture of atoms and molecules, primarily hydrogen and helium, at an average density in the local interstellar medium of approximately 1 atom per cubic centimeter. This sounds negligibly sparse, and at low velocities it is, but at relativistic speeds, each atom becomes a high-energy projectile from the spacecraft's perspective. A hydrogen atom encountered at 99% of the speed of light has a kinetic energy in the spacecraft's reference frame of approximately 7 times its rest mass energy, comparable to the energy of a cosmic ray particle. The flux of these impacts on the spacecraft's forward face would deliver enormous amounts of energy, requiring substantial shielding to protect the crew and critical systems. Estimates suggest that a spacecraft traveling at 50% of the speed of light would need shielding equivalent to several meters of solid material, aluminum, polyethylene, or other hydrogen-rich substances, on its leading face to manage the radiation dose. Cosmic rays present a related but distinct challenge. Galactic cosmic rays are high-energy charged particles, mainly protons and alpha particles, with smaller fractions of heavier nuclei, accelerated to near-light speeds by supernova remnants, neutron stars, and other extreme astrophysical environments. Within our solar system, we are partially shielded from these particles by the Sun's magnetic field and the heliosphere. In interstellar space, this protective bubble no longer exists. Galactic cosmic rays penetrate conventional shielding with relative ease. High-energy protons pass through meters of rock. On a long interstellar voyage, the accumulated radiation dose from galactic cosmic rays would pose a serious cancer risk and could cause significant neurological damage. The problem is not simply solvable by thicker walls. The secondary particles produced when primary cosmic rays interact with shielding material can themselves be highly penetrating and damaging. Interstellar dust particles, tiny grains of silicate, carbon compounds, and ice typically ranging from a few nanometers to a few micrometers in size, present yet another hazard at high speeds. At 10% of the speed of light, a single micrometer-sized dust grain impacts with the kinetic energy of a rifle bullet. At 50% of the speed of light, the same grain hits with the energy of a small, high-explosive shell. At 99% of the speed of light, a single such grain releases energy equivalent to hundreds of kilograms of TNT on impact. On a journey of even a single light year, the number of dust grain impacts would be enormous. The spacecraft would be continuously bombarded by particles capable of punching through unprepared surfaces. The forward shield of a near-light speed spacecraft would need to be a massive sacrificial layer designed to absorb these impacts at the cost of its own gradual ablation, and would need to be thick enough to last for the duration of the voyage. There is also a subtler, stranger hazard. At speeds approaching the speed of light, the cosmic microwave background radiation, the remnant thermal glow of the Big Bang, which pervades all of space at a temperature of about 2.7 Kelvin, would be blue shifted by the spacecraft's motion into increasingly energetic wavelengths. At 99% of the speed of light, the crew would experience the CMB not as faint microwave radiation, but as a bath of hard X-rays, delivering lethal doses in a matter of hours without adequate shielding. At even higher fractions of the speed of light, the CMB effectively becomes a gamma-ray hazard. The universe itself, the background radiation of all of cosmic history, becomes hostile to the traveler moving fast enough through it. And then there is the simply human dimension of the problem, the biological, psychological, and social reality of what it means to be a human being trapped in a spacecraft for years, decades, or centuries. Even in the most optimistic scenarios, a 20% of light speed mission to Proxima Centauri, arriving 21 years after departure, the crew would face isolation of a profundity that no human being has ever experienced. All of human history, all of human civilization has been lived on a single planet, or, briefly, within its immediate orbital vicinity. The deepest solo sailing expedition, the most remote Antarctic research posting, the longest submarine patrol, all of these involve isolation that is, at some level, temporary and reversible. Someone can always be sent to rescue you. A radio message can always summon help in hours or days. Even the most extreme human isolation on Earth maintains, at its core, the possibility of connection. On an interstellar voyage, even a radio message travels at the speed of light. A crew at the midpoint of a journey to Proxima Centauri would need to wait over 2 years for a reply to any transmission. By the time they arrive, more than 21 years will have passed on Earth. Everyone they knew who was over 60 when they left will likely be dead. Children will have grown into adults. The world they departed will have transformed beyond recognition. they will have no ability to turn back. The energy required to decelerate and reverse course would be as enormous as what was required to accelerate. They are committed, not merely to a voyage, but to a fundamental reorientation of their relationship to their species, their history, and their home. The idea of the generation ship addresses the longevity problem, but magnifies the social and psychological ones. If the voyage takes hundreds of years, no member of the original crew will arrive at the destination. The mission will be completed, if at all, by the great-great-grandchildren of the people who began it. These descendants will have been born into the spacecraft. It will be the only reality they have ever known. They will have no personal memory of Earth, no lived connection to the civilization that built and launched the ship. The question of whether such a community could maintain the technical knowledge, the social cohesion, and the motivational will to complete a mission begun generations before their birth is genuinely uncertain. Studies of isolated communities, island populations, monastic orders, Antarctic expeditions suggest that small groups can maintain cohesion across generations, but none of these examples approaches the extreme isolation of an interstellar voyage, and all involve periodic contact with outside civilization. The concept of suspended animation, placing the crew in some form of biostasis to survive the voyage without aging, has been a staple of science fiction since the genre began, and it has attracted serious scientific interest. Certain organisms, tardigrades, wood frogs, some nematode species, demonstrate extraordinary resistance to extreme temperatures and can survive states of metabolic arrest for extended periods. Some human tissues and organs have been successfully preserved through cryogenic storage, but a complete human being with a functioning brain and a continuous psychological identity has never been reversibly frozen and revived. The ice crystals that form within cells during freezing cause extensive cellular damage, and while cryoprotective agents can mitigate some of this, no protocol has been demonstrated for whole organism human cryopreservation and revival. Whether this will eventually be solved through advances in nanotechnology, molecular medicine, or other fields remains genuinely unknown. All of these threads converge on a single, sobering conclusion. Traveling 1 light year, crossing 9.46 trillion kilometers of empty space, is not merely an engineering challenge to be solved by building bigger rockets. It is a confrontation with the fundamental structure of the universe, the fixed speed of causality, the exponential relationship between velocity and required energy, the biological limits of the human body, the psychological limits of human social organization across time. Every approach that might make such a journey possible, antimatter propulsion, laser sails, generation ships, suspended animation, theoretical space-time modification, either requires resources and technologies far beyond our current civilization, or involves physical and social unknowns that remain deeply unresolved. It is worth pausing to put the challenge in perspective by considering the scale of what interstellar travel actually means. Relative to travel we consider routine today, the Earth is about 12,742 kilometers in diameter. The distance from the surface of the Earth to the International Space Station at an altitude of about 400 kilometers is roughly 400 kilometers, a drive of about 4 hours on a motorway. The distance from the Earth to the Moon is approximately 384,400 kilometers, a distance that humans first crossed in 1969 in a journey of about 3 days. The distance from the Earth to Mars at closest approach is approximately 54.6 million kilometers, a journey of around 6 to 9 months with current propulsion. The distance from the Earth to the outer edge of the Oort cloud, the distant halo of cometary nuclei that marks the outermost bound of the solar system's gravitational influence, is perhaps 15 trillion kilometers, or about 1.6 light-years. 1 light-year is therefore the distance from the Sun to roughly the inner edge of the Oort cloud. It is inside our solar system, in the sense that the Sun's gravity still reaches that far, but it is a region so distant that even Voyager 1, having traveled for nearly half a century, has barely scratched the surface of the solar system's extent. The spacecraft we consider our greatest achievement of interstellar reach, Voyager 1, traveling since 1977 and now more than 23 billion kilometers from the Sun, has covered less than 1/4% of a single light year. In the context of the actual universe, in terms of the distances between stars, we have not left the starting line, and yet, this is where the story of human ambition reasserts itself. We have not left the starting line, but we know where the finish line is. We know the rules, we know the physics. We are, uniquely among all the species that have ever lived on this planet, a species capable of understanding the scale of what we cannot yet do. Every civilization that has contemplated the night sky for the past 100,000 years has seen the same stars that we see. The same points of light have looked down on the first controlled fire, on the construction of the pyramids, on the writing of the first alphabets, on the first ocean voyages across open water, on the Industrial Revolution, on the first powered flight, on the first steps on the moon. For all of that time, those points of light were beautiful mysteries, objects of worship and navigation and wonder, but their true nature, their distances, their physical character, the fact that many of them host entire planetary systems, was entirely unknown. In the span of a single human lifetime, we have gone from not knowing that exoplanets exist to having confirmed over 5,500 of them. We have imaged worlds orbiting other stars. We have detected Earth-sized planets in the habitable zones of nearby red dwarf stars, including planets orbiting Proxima Centauri, our nearest stellar neighbor. These are real worlds, confirmed by precise measurement of the slight gravitational wobble they induce in their parent stars and the slight dimming they produce when transiting across the stellar disk. Whether those worlds host liquid water, whether they have atmospheres, whether they have any form of chemistry that could support life, these questions are the frontier of modern astrophysics, and they motivate, with a genuinely new urgency, the contemplation of how such worlds might ever be visited. We stand at the beginning of this contemplation, not the end of it. The Parker Solar Probe represents our current pinnacle of human-built speed, and it falls short by a factor of nearly 2,000 of what would be needed to reach Proxima Centauri in a human lifetime. But 100 years ago, the fastest object humans had ever built was a propeller-driven biplane, and nothing had ever escaped Earth's atmosphere. 60 years ago, no human being had ever left the surface of the Earth. 50 years ago, we walked on the moon. The exponential pace of technological progress in aerospace and physics does not guarantee that the gap between our current capabilities and relativistic travel will be closed in any particular time frame. It may never be closed, but it does mean that the distance between our current best and what physics permits is not a fixed, permanent fact about human capability. It is a gap with a history of shrinking. There are researchers today who study the physics of warp drives in academic settings. There are engineers designing laser arrays that could, in principle, accelerate tiny spacecraft to 20% of the speed of light within the next few decades. There are physicists probing the properties of exotic matter and negative energy density in quantum field theory. None of this work guarantees success. All of it reflects the extraordinary fact that our species has, for the first time in its history, identified the specific physical barriers between where we are and the stars, and begun, in earnest, the work of thinking about how to cross them. 1 light year, 9.46 trillion kilometers, the number we began with and the number that has accompanied every step of this exploration, growing not smaller as we examined it more closely, but somehow larger, richer, more textured with implication. At walking speed, it is a journey of 215 billion years. In the fastest spacecraft ever built by humans, it is 18,000 years. Under the constraints of known physics, brought to their absolute extreme with technologies that would surpass our current civilization by orders of magnitude, it might be compressed to a matter of days for a sufficiently fast traveler, but never to less than 1 year for the outside universe through which that traveler moves, because light itself takes 1 year to cross 1 light year, and nothing travels faster than light. This is what the concept of a light year ultimately expresses. If you follow it all the way down, the universe is separated from itself by the limitations of causality. The stars are so far apart that even the information of their existence, encoded in light that left them years or centuries or millions of years ago, takes cosmological spans of time to reach us. We see the night sky not as it is, but as it was. The light from Andromeda entering your eyes right now left that galaxy 2.537 million years ago, when our ancestors were early Homo habilis, chipping stone tools on the East African savanna. We look at the sky and we look into the past. The distance of 1 light year is not merely a measure of space, it is a measure of time. It is the universe telling us, in the precise language of physics, how long it takes for the news of any event to travel from there to here. It is the universe's postal system, and the postage rate is a year of waiting per light year of separation. Everything we know about the stars is old news. Everything they know about us, if anything out there is capable of knowing, is equally delayed. In this context, the act of sending the Voyager spacecraft, those remarkable aluminum and electronics artifacts, now drifting in the interstellar night at 17 kilometers per second, takes on a meaning that transcends its literal distance covered. Voyager 1 will not reach another star in any human time frame. It will not be recovered or intercepted or greeted. It carries its golden record and its cache of human knowledge into an emptiness it will travel for billions of years, long after the sun has expanded into a red giant and consumed the Earth. But sending it was, and remains, a statement, a declaration, a proof that we know what is out there, that we know the scale of the distance, and that we sent something anyway. The universe is 13.8 billion years old. It is 93 billion light years across in the observable portion. It contains hundreds of billions of galaxies, each containing hundreds of billions of stars, orbited by hundreds of billions of planets. Against this backdrop, the distance of 1 single light year is almost nothing, a rounding error, a decimal place too small to register on the scale of cosmic structure. But for us, for a species that evolved on one planet, that first looked at the sky with wonder from the floors of savanna grasslands, and later from the decks of sailing ships, and later still from the windows of orbiting spacecraft, 1 light year is the edge of the comprehensible. It is the place where our instincts run out and where physics must take over. It is the point at which the scale of the universe stops being a fact and becomes a feeling. The specific feeling of standing at the boundary of everything familiar and looking out into something that does not care about your timescale, your engineering, your ambition, or your longing. And it is precisely because that boundary is so hard, because crossing even a single light year requires confronting the deepest and most uncompromising laws of physics, that the act of genuinely understanding 1 light year, not merely stating the number, but tracing all of its implications through the length and breadth of everything we know, is itself a kind of crossing, not of space, but of scale, a recognition that we are small creatures in a vast universe, that the universe does not scale to us, and that we are, somehow, aware of this. We are aware of our own smallness. We have measured the distances that dwarf us. We have understood, with the full precision of mathematics and experiment, exactly how far we cannot go. That understanding, that exact, quantified, scientifically rigorous awareness of our own cosmic insignificance is perhaps the most distinctively human thing there is, and it is where every honest exploration of the universe's scale must end, not in despair at the distances, but in wonder at the fact that we know them.